Okay.
streaming.
I think we're live. Can you check?
Yes.
All right. Hello, everyone. Welcome to today's episode of Quadcast. I am your host, Tim.
And this is Sile. Welcome, everybody. Our co-host Mikey may or may not be joining us due to certain other obligations, so he might pop into the episode very surprisingly. So stay tuned to find out what happens. If you haven't already, do join our Discord channel. And if you're watching us on YouTube, where we try to do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, to ask us questions during the episode. So let's get to it, Tim. Um, I guess like one thing I'm curious about is like I've been reading a lot of articles. They talk all about these infinities and stuff, and in some previous episodes we've had talked about how infinities don't really exist in nature, that they're essentially like more of approximations or artifacts. So I guess can we like maybe start off by talking about like how infinities arise in physics, starting from like high school physics to like, modern particle physics as you see today, and like what that tells us.
Yeah, absolutely. So infinity is sort of like a mathematical concept. You can think of as a number, but it's not really a number. It's something that's larger than everything. And obviously in real life we cannot measure infinity. Like take a camera, take a computer, you're never going to get an infinite result, right? You just get some really, really large number. That's the closest thing. But a really large number is still far away from infinity. If you would like infinitely far away from infinity still. So, but but starting from high school physics, I think a lot of students, myself included, already noticed some interesting behaviors. Like for example, if you look at gravity, right? If you take high school physics, you look at gravitational attraction, you might study certain equations that tells you that the energy between two objects, if they are attracted to gravity, goes like 1 divided by the distance. Then of course it's very natural to ask, well, what happens if the distance go to 0? When you have two objects infinitely close away. But of course in mathematics, you get something like 1 divided by 0. You get the dreaded infinity, right? So situations like that comes up again and again, and also in astrophysics, you can ask the question, how large is the universe? And Einstein famously coined, the only thing he thinks might be infinite is, the universe, and the other one is human stupidity, but we won't comment on that. So it's hypothesized that the universe is infinite, but really you can't observe an infinite universe, right? You can see stars and try to make a guess how large the universe is. It's a pretty darn large number, right? Like 13 billion light years away, but it's still not infinite. So in many instances, we see that the nature of infinity comes from equations, not from observations. So there's a little bit of discrepancy there. Like physics is a practical discipline. Our equations are supposed to describe reality. And so when equations have infinities, but reality does not, there's a little bit of reconciliation that needs to happen there.
hmm Well, I thought physics theories are supposed to be based on like physical things. So I guess like where do like why is that infinities arise?
Yeah, I think we can talk a little bit about this. This is related sort of to the previous episode, right? Like for example, you
Mhm.
can argue that the gravitational energy between two objects is 1 divided to this. It's proportional to 1 divided by the distance, right?
Mhm.
Like, does it really make sense to take it to the extreme when the distance is 0? Like, probably not. So the law, you can argue that this law of gravitation, Newton's law, is only approximate, so that you'll never plug in 0 to get an infinite
Mhm.
answer, right? So
Mhm.
this tells you that, look, these physical laws have regimes of validity, and usually the infinities are away from the regime of validity of our theories, because our theories are approximate. And that's sort of the first level of reconciliation. It's just that, look, infinities can't possibly make sense. So it means that it must be, whenever infinite answers come out, they must be excluded from the regime of validity of our theories. And that's actually typical for almost every theory that we've studied.
Ah, I see. I see. So you're saying infinities is there because it's more due to these approximations that we make,
Hmm.
such as like the one over inverse distance laws that, Newtonian mechanics for gravity, electromagnetism and whatnot. You're never going to really explore the distance where like never going to explore the regime where the distance is zero. Otherwise, then like, that isn't valid within the regime of what it talks about. Is that fair?
Yeah, yeah. I mean, you can almost argue it this way, right? Imagine you look at the energy between two charged particles and you bring them closer and closer and closer, right? At some point,
Mhm.
the energy will become so large, even larger than the entirety of the universe. I mean, there's got to be some upper bound. Like a good analogy,
Mm,
I think it's like for example, you can look at the income of the individuals in the world, right?
mhm,
You might see that, hey, there's a lot of people that has a lot of money, right? Or the multi-billionaires. And if you try to
mhm,
model this distribution, you might find a lot of tails, right? Your distribution
mhm,
might look like one over the income, something like that. And when you do
mhm.
this modeling, theoretically, you could have people with infinite money, right? Like it's not
Yeah.
forbidden. There's a very very low chance, right? But it doesn't
Mhm.
mean that in real life there are actually people with infinite money. Like, you can't.
Yeah.
I don't think the U.S. can print quickly enough. If someone have infinite, so at some point your model has to break down because we
Yeah.
have finite amount of money in the world, and we believe the same thing is happening in physics, right? Like it's like, look, if the energy between two objects goes like 1 over r, there's gotta be some threshold in which the theory breaks down. I mean, that's not to
Mhm,
take away that, hey, look, at some point when the distance is very small, the energy could be very, very damn large, very, very large, but just not
mhm,
infinite, right? So it could be large, but not infinite. And at some point, it becomes so large that the theories that we have, it's not valid anymore.
mhm. I see, I see. So let's kind of like, I guess, go through the history of this. So we've been talking about so far the high school physics perspective, where you have like
Mhm.
particles that interact with each other, and their interactions are some one over some distance, like essentially inversely proportional to distance or distance squared, whichever one of those. And then that assumes that these particles are point-like, meaning they basically take up almost no space. And when you bring them in like close together, there's with their zero distance, it blows up, meaning that the amount of interaction goes to infinity, which we agree is nonsensical. Now, if you were to zoom in, you would notice that like, okay, they're not exactly point-like structures. Quantum mechanically, they have some sort of structure that takes up space. So I guess like if we look at that, do infinities arise in other ways besides like this one over, r squared or one over r, this one inverse distance thing that you're talking about?
Yeah, I think this inverse distance is a very good example.
Mhm,
And it does come up, I think, in other more intricate ways.
mhm,
Particularly in particle physics. For example, you can look at the energy in the vacuum of particles popping in and out, and this we
mhm,
described in the past. In quantum physics, the more you zoom in, energy kind of scales like 1 over the distance. I guess it's sort of similar, similar logic.
mhm,
So if you zoom in the smaller and smaller, you get more and more of these energy fluctuations, and at some point it
mhm,
blows up. So it's a
mhm,
very similar behavior, and I think the infinity associated with the universe. I don't know if it's exactly the same. It's somewhat similar, right? Like
mhm,
look, every physical system has some finite volume, right? Like you run an experiment, your experiment might be in a university, right? It's got, I don't know,
mhm,
1,000 square foot or cubic feet of volume, whatever, right?
mhm,
But when we do physics, it's really hard to deal with these finite volumes of fact. So we just assume the space you're in is infinitely large. It makes the math
mhm.
easier. And
Mhm.
so there's also some infinities coming there. But I think the one over distance is quite analogous in many situations. It's kind of like that.
Hmm.
I don't know, Mikey, would you agree?
Yeah, I think that's the most important infinity that we see again and again and again, and
Yeah, yeah.
that's kind of like the fundamental crux of particle physics. But the infinite universe thing, that's how do we think about that? I
It's
mean,
hard to say, right?
we like to assume that the universe is infinite. There's no real reason to believe that the universe is infinite, just because we can't really observe or detect any kind of a physical boundary. And as Tim mentioned, because it makes the math easier. Um, it's like a reasonable construct, just to imagine that. But I don't know. I think it's dangerous to take it too seriously.
Yeah, I think so. Yeah, but I think in particle physics, because we are more interested in zooming in smaller and smaller stuff.
Mhm.
So the energy blowing up this level of infinity is kind of the most, I guess, problematic, if you like, at least theoretically.
Mhm.
And at least the theory needs to somehow deal with it, right?
Mhm. So can we take a step back and sort of look at this, like, what does this physically mean? Like, so far we've just talked about
Mhm.
equations, like equations are blowing up, but in nature this doesn't happen. So like, what does this actually mean? Why is this happening? In some sense. Like, I mean, you've explained it
Yeah,
mathematically, but like, yeah.
yeah, and because physics is experimentally driven, then
Hmm.
this must be an artifact of our theory, right?
Hmm.
And so for example, you can say, hey, look, if 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 you get closer, let's say to an electron, the energy goes
Hmm.
like 1 over the distance. The closer you get to the electron, the more energy you feel. You might say, hey, doesn't it tell you something about the intrinsic energy of the electron itself, right?
Hmm.
And then you can make this argument and say, well, if you try to do a very naive calculation, you look at the intrinsic energy of the electron, which also
Hmm.
comes from this, this electric field around it, which gets very large when you get close to the electron. You could argue that, look, the intrinsic energy of the electron must be very large. It's dictated by a very large number, because it's not quite infinity, because
Hmm.
infinity doesn't exist in nature. But at least our theory should be reasonably okay, good enough that it's a okay approximation. Then you say that, look, it must be quite large. This energy within the electron. So it's a very large number. But now you ask the question, well, experimentally, we don't measure what is large, right? I mean, the electron, the energy of the electron isn't very large. The electron has a mass. So presumably, if you
Hmm.
follow Einstein's theory, E equals mc squared,
Hmm.
the energy of the electron should already be folded in to its mass, which is not very large in terms of particle physics. We have particles that are way more massive, like the proton is way more massive than the
Hmm.
electron, right? So you can say, well, how in the world, that's a discrepancy in the theory, right? You have a very large number, but what you measure is very small. Then you argue that in your theory there must be some level of cancellation,
Hmm.
because because the experimental fact tells you that it's small. So in your theory, you just say, well, there must be some cancellation now. So there must be a large number minus another large number that gives you a small number for the electron, right? So the thing is, this is totally fine. It's completely fine for a theory, because we measure the mass of the electron. We don't measure the large number 1 minus the large number 2. Those are not measurable in some sense, at least not yet. But you only measure the difference at the end. So theoretically, it's completely okay. It's a theory that can make sense. But the only thing that's left is this conceptual issue, and what we call fine tuning.
Mm. So before we go towards fine tuning and this stuff, can we explain to the audience what does it mean to like get closer to an electron? Like, if I go closer to my hand, like, like how close do I need to be, or like what does that even mean? And then also, I don't want to take it for granted that energy goes as one over like a distance. How does that arise? Like, what's an intuitive way to explain that?
Yeah. So when we say getting closer, I guess those are two separate questions, right? Like, so
Mhm.
when
Yeah,
we
yeah.
say we get closer to something, we literally just mean like when I put my hand against the wall and I touch the wall, like
Mhm.
we usually think of that as like direct contact. But if you look very closely, you see that the atoms of my hand are not actually touching the atoms of the wall. There's
Mhm.
some kind of electrostatic repulsion, basically like a force field that's preventing my hand from making contact with the wall. In
Yeah.
order to overcome that, I need to apply a very large amount of force um, against the wall if I want to overcome that barrier. If I actually want to make the atoms of my hand get within a very, very close
Mhm.
distance of the atoms of the wall. Um,
Mhm.
and so this is why we make atom smashers. The goal of an atom smasher or particle collider is essentially to try to overcome that barrier, to try to get two things as close to each other as possible, just to see what happens when they get very close.
Mhm.
Yeah, and I
So,
And the second question,
yeah.
sorry.
I'll go, Tim.
Oh yeah, I was gonna say yeah, and the audience might wonder why does that have to do with self, the energy of the electron itself, right? Because if you imagine you just remove, imagine the electron just poof out of existence, you just remove it, you totally will not feel this repulsion anymore, right? So the presence of the electron creates this repulsion or attraction, and so the self energy or the mass of the electron must encompass all the influence that the electron has on everything else, and that includes distance that are very large to distance that's very small. So that's why we kind of have to look at all distances. So things that are far away will make a contribution. Things that are nearby will also make a contribution. You kind of have to sum it all up in order to kind of get the kind of the intrinsic energy of the electron, and that's why you're faced with this infinity, right? When you have to sum up the contribution from getting really close as well. So
Mhm. Mikey, you were about to answer the second question. The why does energy go as like inverse
Yeah. I
distance?
just want to just like, yeah. Like, because I don't know if you guys already talked about this before I got here, but yeah. So you're asking about this, you know, relationship between energy and spatial distance.
Hmm.
Uh, Energy, I guess you talked about how energy is like one over spatial distance. Or said another way, high energy is always related to short distances,
Yeah.
and vice versa. Large distances are always related to low energy. And the reason why that's such a fundamental truth about physics is just because everything is made out of waves. Everything
Mm.
in the universe is a wave. And the thing about waves is that if the wave is a large wave, it's like a lazy large wave. It's very slow. It has very low energy. If you imagine a wave that's like furiously wiggling up and down, then that's a very energetic wave, and the wavelength of that wave is very, very small. So small wavelength waves are high energy. Large wavelength
Mm.
waves are low energy. And so because everything in the universe is a wave, you get this very, very fundamental relationship between energy and distance, where short distances correspond to high energies and large distances correspond to low energies.
Mm. That makes sense. That makes sense. Yes. So if we kind of combine these two concepts together, what we're essentially saying is that like you have you have energy that depends on like energy that depends on this inverse relationship of distance. And as you get like closer and closer to something, it gets a bit more I guess like yeah, I guess I'm trying to understand like what is it about like getting closer and closer? Oh, actually, yeah. Let me actually rephrase my question. So when you collide two particles together, like two protons together in like the LHC and whatnot, they can't actually touch because if they, I mean, can they actually touch, or like what does it mean for them to actually touch? Like, does the model of like 1/r get broken? Is it something completely different? Like, kind of what happens with that if there's like this
Yeah.
electrostatic repulsion between the two?
Yeah, so let me answer this. So they do experience some level of force law. It might not exactly be 1 over
Mhm,
r, so there will be some
mhm,
distant dependence. And they never exactly touch. You can roughly estimate how close exactly they get. Of course, the more energy
mhm,
you have, the closer the two particles can go through. And then the smaller and then the closer they are, the more, I guess, intimate that these protons will feel the internal structure of the other proton, and then you get interesting interactions happen, right? So the 1/r dependence, like Mikey was saying, is a very reasonable law to expect. Experimentally, this is something that you can do experiments in high school physics to extrapolate this, right? You can look at two charged sphere to see how much they attract each other. So it's a little bit of an extrapolation, right? Like you run an experiment, you see how the forces behave, then you can extrapolate, well, a little closer, do they still behave the same way? And you can extrapolate further and further and further. And keeping in mind that whenever you probe smaller distances, there's a higher chance that new physics could emerge. Because look,
mhm,
our experiment is not perfect. Like we don't know the makeup of the entire universe, all the possibility that exists. So every time we run an experiment, you can only probe up to a certain energy scale. Like we only have so much energy to give, right? Like all you add all the power plants in the world, that it's not enough energy. You could still go more, right, in the universe. So we
mhm.
hit some upper bound in terms of how much energy we can probe, and that corresponds to a lower bound on how small the stuff is, how much resolution power we have, like how small the pixel is when we look at these particles, right? So the laws that we have so far are kind of limited by those resolution effects, right?
Mhm. I see. I see. So the laws which we form are limited by resolution effects. And so I guess like what is the issue with like how does this tie towards infinities? Like if you can only
Mm.
go to a finite resolution, I guess like what does that mean with these infinities that arise? Like how are they connected to each other?
Yeah, I think you can say that for example, imagine you probe at energy. What's a good unit? I guess at the LHC there's like 14 TeV, something like that. Uh, um,
Mhm.
1 million
What's a
times.
TeV?
It's
Oh,
it's
go
a
sorry.
it's a
No one knows what
tera.
a TV is.
Yeah, tera electron volt. It's 1,000 times the mass of a proton. I think that's a good. You look at Einstein's equation, energy equals mc squared. So you convert the
Hmm.
mass of the proton into energy, right? So imagine you have an energy upper bound around, let's say, 10,000 times the mass of the electron, right? So what does that have to do
Hmm.
with infinity? So I think if you have this experimental input, then you can roughly argue that when you say infinity, you have to say like how much infinity, right? Um, so if I have 1 over small distance, you can convert that roughly to energy. Um, so it means that if I have some numbers in my theory that calculate that is infinite, it might actually correspond to, depending on the unit of what things I'm measuring. If in energy, that means that the most I can say, the largest number I can comfortably say that this is, because we don't measure infinity, the largest thing I can say is maybe it's um, uh, 10 TeV, right? Because that's how much energy I have. That's how much energy I'm probing. Um, so so really, experimentally, we don't measure infinity, but we can measure roughly how large these numbers could get experimentally, and
Hmm.
then we can say, well, and we kind of look at the discrepancy, right? Like so let's say we have the self energy of the electron, and we probe up to 10 10 10 TeV. So you know that there's a contribution to the mass of the electron, maybe around 10 TeV, right? But the electron is way smaller than that. So we know that there's a cancellation between 10 TeV and some other number to arrive at the small electron mass. And actually, electron may not be the best example because it doesn't exactly cancel like that. But that's experimentally, that's what it means. You know, when you measure something at an energy scale, what you can say is how much cancellation is happening. That's what you can measure. But the mass of the particles don't change, if that makes sense.
Yeah. So I guess let's kind of like examine that a little bit more. When we talk about mass of particles don't change, actually, Mikey, what does it mean to measure mass? What is that like? How does that even work?
To measure mass?
Yeah, like what does it mean to measure mass? Like, do I put the electron on like a scale, like, and weigh it, and then like ask it to go on a diet, or like what?
Well, okay, so I don't know, like, okay, I don't know how this is connected to how you measure it in experiments, but so, okay, but the way you always measure mass in some sense, I assume, is you apply some force to
Okay.
the object,
Mhm.
and you see how that object moves as a result of that force. Um, a larger mass object will require more force to move. A smaller mass object will require less force to move. So you apply a force, and you know how much force you applied, and you see how it reacts. And in some sense, that's the most fundamental way to measure what the mass of an object is. And that actually brings up kind of another kind of infinity, because if you take that seriously, right? So what did I just say? I said the mass of an object, if it's smaller, it takes less force to push it fast. They can go fast, right? So what happens if the mass of the particle goes to zero? Then it should take infinitely small amounts of force to make that particle move infinitely fast, right? Like imagine I try to push a truck, or
Yeah.
I have to apply and I apply some force. It's not going to move very much. But if there's a marble, I apply some force, it's going to move fast. As I think about smaller and smaller mass objects, it takes less and less force to make it move even faster. And we know that some particles have no mass. So that might lead you to believe that an infinitely small force could make this thing move infinitely fast. But because the speed of light is a cosmic speed limit, the object can't move infinitely fast. The fastest it can move is the speed of light. And so this is kind of another conceptual place where you would think in infinity, if you didn't know anything about relativity, you would think that you could push these particles infinitely fast, but you find no, there's actually an upper bound on how fast they can move, which we call the speed of light.
That makes sense. That makes sense. So Tim, like coming back to this, I'm wondering, like, when you talk about two things subtracting each other, what is like the big thing, this like really ginormous number, and what is like the slightly less ginormous number that you're subtracting such that you get like, let's say, mass of whatever particle you want, or maybe charge, or all these quantities that you're trying to measure? Like, why in the theory are there even infinities when, like, in experiment, like, clearly the mass of an electron or whatever particle you're looking at is like finite and small?
Yeah, it's a very good question. The real answer is we don't know. And the reason you ask why is there a cancellation, because it needs to be, because the physics model has to explain experiment. So if the theory predicts, let's say, the mass of an electron, or probably the better particle is the Higgs boson, because of the way the mathematic is, the mass of the electron is actually logarithmically sensitive. So there's no subtraction, but this is the technical detail that I don't want to get into, right? But the mass of the Higgs boson, it has this ginormous cancellation. So basically, in the theory, you see that you might see, 100 million minus 100 million and 175. You might see that in order to give you the right Higgs mass. Oh, sorry, the Higgs mass is like 125, right? So the 125 is what you observe. the 100 million you don't observe. Your theory predicts there's some very large number, or more precisely, the theory predicts infinity, but you know there cannot be infinity. So the next best thing is like, well, there's got to be some very large number. So we don't really know where this cancellation is happening. We don't really know where it comes from. But the theory has to postulate it in order for the theory to actually be sensible. Otherwise, this theory is nonsense, right? It'll predict that all the masses are too large, right? So the theory has to find a way to accommodate these subtractions. And that is what happened with particle physics. In particle physics, we describe a lot of particles and their properties. A lot of the properties of these particles are actually not very well explained. And a lot of them comes from one large number subtracting another very large number and somehow give you a very small number. The current theory of particle physics does not explain where the cancellation comes from. It merely explains the experiment. So it explains the how, but not the why.
Yeah, it seems to me like you're computing some really large number and then measuring it relative to some other slightly smaller large number. One question I have is, where does a slightly smaller large number come from? Like, you just can't like compute a big number then arbitrarily subtract out like, oh, I'm going to subtract this out so it matches the experiment. Like, it has to fit theory. So where do these two, like, I mean, can you give us an example of like, where do these two numbers come from in like a calculation? Like, I would assume maybe one is like, oh, like, I mean, could you think of it like, oh, like, I have a, infinite space where I put an electron in it. I measure the mass of it in this infinite space. And then I look at the infinite space without the electron and compute something involving that and subtract these two quantities and I get the mass of an electron.
Yeah. I think the answer is these terms actually come from very different places. And it is one of the mysteries of particle physics, right? And like, for example, if you look at the mass of the electron, one contribution could be coming from, let's say, electromagnetism, right? Another contribution could be coming from gravity, because the electron, can feel gravity. It can also feel electromagnetism. Another contribution could be the weak force, right? Because the electromagnetism and the weak force are one and the same. And another contribution could be the Higgs boson, right? So we're not just actually talking about one large number minus another large number. It could be one large number, subtract another large number, plus another large number, minus another large number, plus and minus, like many, many terms coming from many different places, like apple and oranges and grapes and strawberries and all kinds of different terms together. And somehow they add up to the experimentally measured value, right? And that's where they come from. And it's not... And just like you, physicists are very bothered by this fact, but it's just a brute fact.
So are you saying the way that physicists deal with infinities in like modern particle physics and the way you described it is like hope that their theory will produce a cancellation of like two, loosely speaking, things that tend to infinity, subtracting each other in such a way to give you like a small finite result? We're adding together, subtracting, and all these numbers you're adding together.
Yeah, pretty much. And I would say that it's not a hope. It's a demand that it has to work, because otherwise your theory is wrong. So in order for so I don't know. I think Mikey has maybe had a different thought.
I don't know. So when you're like, so I guess for the last like 40 years, one of the guiding principles that has been driving theoretical physics development, especially particle physics development, is the idea of a symmetry. If you have a really large positive number and a really large negative number, and they happen to be almost exactly the same, that's what we call a symmetry. And when we observe this happening in nature in calculations, we would say that, oh, like, so there's some, it's like, like a symmetric shape, like a triangle. It's exactly on the left side is exactly the same as the right side. You can think about similarly as like this large negative number, this large positive number canceling each other out. And so these are kind of like the principles that we use to build the theory. And sometimes when we see this happening, it's puzzling. We can't find what symmetry is responsible for this. As Tim mentioned with the Higgs boson, we are what's the word? We are
Confused.
exhausted with the search for a symmetry to explain why this happens in certain cases. So in some sense, I think it is a hope, right? Like a lot of physicists hope that this kind of cancellation, the existence of these kinds of symmetries, should be a fundamental principle of nature. But I would argue that maybe we're coming to a point where we're seeing that this is not always true.
Yeah.
So I don't know.
Yeah, let me just add that it's not maybe I didn't frame it properly. Sometimes large numbers do magically cancel, like Mikey was saying, with symmetries, right? Like, for example, in electromagnetism, you can argue that whenever there's a particle that's positively charged, because of the restriction of the forces, there has to be an equivalent particle that's negatively charged, right? So this fact, for example, can be linked to why matter and antimatter has the same mass, right? So sometimes some cancellations can be perfect, right? Like particle and antiparticle, they have equal and opposite charges, and when you add them up, they will cancel in some ways. So that's why things like the mass of electrons has a little bit of the subtraction is a little bit less severe, right? It's logarithmic, like I was mentioning before. So this is a case where symmetry actually help reduce some of that sensitivity. Also, it's a very technical thing, right? It tells you that there's a way to organize these large numbers where really, in reality, there are no large numbers. It's just an artifact of our calculations. But like Mikey was saying, yeah, there's always going to be this tug of war. You know, do we interpret our equations naively as they are? So there's really large very large number close to infinity, minus another very large number close to infinity to give you this tiny residual. Or maybe there's some hidden reason for this to happen. We're just too ignorant to think of it the right way. And then maybe these weird cancellations will not happen. So that's pretty much what physicists have tried to do for the past, like 50 years, is to find these patterns. And sometimes actually we've been quite successful, but there still remain a few remnant cases where this technique does not work.
I guess like just to kind of double click on the whole symmetry argument. This doesn't seem very symmetrical to me because like I would assume that if you had a like large positive number and a smaller slightly smaller large positive number and they subtract them and you don't get exactly zero, there's not exactly balance. So is this like an approximate symmetry, Mikey, or what do you mean by symmetry in this context?
Yeah, I would call exactly what you described an approximate symmetry.
Okay. That makes sense.
It's like a
I guess
perfectly
like
symmetric triangle, but there's a little kink in it. There's a little kink in it that makes it not perfectly symmetric, and that's what makes us here.
That's fair. So I guess like Tim, coming back to what you said about like it being, that this it's actually like this whole cancellation thing seems like it's been like, working in certain areas, but where does it just like fail? Like just utterly just does not work at all.
With the Higgs boson and with dark energy.
Yeah,
Those are the two places where it fails completely.
Yeah, I mean, and also perhaps a real life example like could be the lottery, for example, right? Like you can argue that hey, for example, hey, let's say I won the lottery. You might argue that, come on, dude, Tim, you never buy lottery tickets, and what's the chance that you just happen to win the lottery? Maybe I must know some criminal minds to just kind of rig the lottery system to give me the right numbers, right? Or another perspective, it could be that, look, dude, there are millions of people in the world playing the lottery, and the reason why you're hounding on me is just because by chance I really did win the lottery. If I didn't win the lottery, you wouldn't have be asking this question in the first place. So so there's this tug of war where, hey, look, maybe these cancellations are real. Maybe they are really just kind of, we got lucky. It just the stars happen to align such that the universe exists, and we humans are here to question it. So maybe there's a little bit of a selection bias here. So in this case, yeah, then the whole argument will fall apart, and we're just wasting time trying to figure out why we have like some large number minus another large number. Maybe it's just a fact of life. So it could be plausible, but we don't know.
Gotcha. I guess like you know, to any like budding theorists out there, for lack of better words, what would you say like infinities actually represent? Like mostly when I think of infinities, I think of like very large numbers, problematic, dividing by zero. Like when a physical theory has an infinity in it, is that actually what it means, or is there something deeper of what it means?
I think for me, there's a one word summary of what infinities are. It's ignorance. It just tells us that we
Oh,
don't
that's
know.
what I was gonna say.
Did I steal? Did I steal your word?
Yeah, that's totally what it is.
Come up with a better one. Is there a better word for this?
Anyway, go ahead, Tim.
I guess ignorance, you know, infinity is a way for us to say we don't know. And that's true for the self energy of a particle, you know, the size of the universe, and even like singularities in a black hole. It's just saying it's just a word that tells us, hey, look, our theories are breaking down. It's outside of the regime of validity of our theories. And I mean, of course, you can think of it negatively, like, oh crap, our theories are terrible, right? But every theory has that, right? We're not perfect, right?
Yeah.
So I think the alternative perspective is warranted. It tells us that there's something interesting going on, and I think that's a physicist's perspective. We should chase these infinities, chase them down, and see really what's going on. And I think history has told us that usually we find interesting answers. So.
That makes sense. Well, we're almost at time, and I want to give you guys a chance to leave any concluding thoughts. Tim, since you spoke, I'm gonna pass it off to Mikey, just very abruptly. Put you on the spot, Mikey.
Yeah, no, I mean, I was just thinking about this recently, about the fact that there's no infinities in nature, and I think, I don't know, this isn't like my only takeaway, but I guess the thought that's been kind of tickling me lately is that, people have thought a lot about like done a lot of thought experiments about the implications of an infinite universe, and I think my feeling now is that all of that is stupid and it's a waste of time, because yeah, there are no infinities in nature. And if you imagine there's an infinite universe, you run into all kinds of kind of weird conceptual issues. And I used to, just like any other physicist, like I used to spend a lot of time thinking about those weird conceptual issues as well. But it's just a waste of time. The universe is almost certainly not infinite. What is out there, we don't know, but I think I can just reliably say that the universe is not infinite at this point in my life.
I think that would be a separate podcast episode to debate that, because I know several people who subscribe to that notion, or rather because we don't know. It's like it's possible, but unclear. I will maintain an agnostic position on this one. Anyway, Tim, go ahead.
Yeah, I don't think I have much to add. I think we just don't know. I mean, well, at least one thing we know, that there's nothing that's infinite for real. I think that's something to keep in mind. Something always stops you. There's no infinite money in the universe. It always gets stopped.
What about human stupidity, Tim?
Then I think this analogy is even better. It signifies our ignorance, I think.
The only thing infinite is our ignorance. Would you agree with that? Would you agree with that?
I think that there is only ignorance. I wouldn't say that's infinite. Ignorance is ignorance. So
fair enough. Well, On that note, I want to thank everyone for joining us, and we'll see you all next week.
Yeah, see you all.
Yeah.
Okay, bye.
Bye.